Hello, and welcome to Lesson 2 of this Introduction to Linear Algebra with Wolfram U. The topic of this lesson is Systems of Linear Equations. So let's begin with a brief overview of the lesson. So in this lesson, we'll review systems of linear equations such as the following. So you got two equations in the unknowns x1 and x2, x1 plus 5x2 equal to 7, and 2x1 plus x2 equal to 5. And we'll do two things with them. The first thing we'll do is to try and show how you can represent such systems using the matrix notation. And the second thing is we'll talk about how you can solve these systems using the Wolfram language. Now you might say, oh, this material is very familiar to me, but it's going to be very important for future lessons. So it's quite important that you pay attention to the lesson and get all the details right. So let's begin with something even simpler, namely the topic of linear equations. So a linear equation in some variables x1 up to xn is a relation of this form. And the coefficients over there, a1, a2, up to an and b, could either be real numbers or even complex numbers, but we don't need to worry too much about that in this course. So here's an example of a linear equation, 2x plus 5y equal to 7. There are two variables, x and y. Here's another example of a linear equation. So it's got three variables, x, y, and z in it. But on the other hand, there are two examples over here of equations that are not linear. They are non-linear, as we would say. So the word non-linear means anything that's not linear. So the first equation has an x square in it, so that cannot be linear. The second one has got a square root of y in it, so it cannot be linear. Now, that leads us to the idea of a system of linear equations, which is just a collection of linear equations put together. And you still have n variables, right? So you have a system of two equations over here. And the question is, what does it mean to say we have a solution of such a system? So solution is just a list of numbers which make each equation in the system a true statement when you plug back those values for the variables. So here's the same example from the top. And if I plug in x equal to negative 8 and y equal to 3, then you see that you actually get back true and true. That says that this is a solution of the system. But on the other hand, if you plug back 2 and 1 for x and y, then the first equation is satisfied, but the second equation gives false, which means that this is not a solution. Now, of course, a linear system may have no solutions or one solution or many solutions. So together, we talk about the solution set of such a linear system. Okay, so on to talking about matrices and matrix notation. So matrix will be represented using a nested list in the Wolfram language. So each list in this list is actually a row of the matrix. So for example, here is a matrix. It's got 3 rows and 3 columns. So right out we have a list of lists. The first list in the row over here is just 3 to 1. Then you got 4 to 3, and then 1, 4, 1. Okay, now if you want to view the matrix in a traditional notation, a traditional matrix form, then you can use the matrix form function, and you get back this nice display which has got the first row as 3 to 1, the next one is 4 to 3, and third one is 1, 4, 1. So matrix form is a nice way to display matrices in the Wolfram language. And then some terminology. So when I say that something is an M by N matrix, that means it's got M rows and N columns. So for example, here you got a matrix which has got 2 rows and 3 columns, so it's a 2 by 3 matrix. Question is, how do you find out how many rows and columns? Well, you have a nice function called dimensions. So here's the same matrix named as capital A, and if you do dimensions of A, you get back 2, 3, which says that there are 2 rows and 3 columns in the matrix. Another kind of matrix that's important is a square matrix, which is one which has got the same number of rows and columns. So here's a 2 by 2 square matrix. 2 rows and 2 columns, and you can check that with the square matrix Q function. Q means that you get back a true or false. So square matrix Q of that matrix will give back true, which says that this is indeed a square matrix. So with that background, we can now talk about matrix representations of linear systems. So a linear system can be represented very compactly, very simply by using matrices. So here's a system of 3 equations. It looks quite messy, but once you use matrices, it all starts looking very simple. So the first equation has got coefficients 1, -2, 1. Second has got 0, 2, and -8. The third one, -4, 5, and 9 on the left-hand side. So that's the matrix called the coefficient matrix of the system. So capital A is the coefficient matrix of the system. And of course, you can examine it, and you get back just the same matrix that's shown over here. But you might also want to include the right-hand sides, 0, 8, and -9, and then you get back what's called the augmented matrix of the system. So here is the augmented matrix, and here's the matrix form, which looks correct. So the main point is that the last column of B, 0, 8, -9, will represent the constants on the right-hand side of the equation. Okay, so now the next point over here is that you can solve such a system using the function solve. So solve is very much like what you do by hand, namely just write on the system as given to you in a list. You give it to solve, and then you get back the solution. In this case, x is 29, y is 16, and z is 3. But you see it's a list of lists, so you can extract the first part of that using the part function. That's the part function. And then you can plug it back over there, and you see you get back true, true, true. That says that all the 3 equations are satisfied by the solution. So x is 29, y is 16, and z is 3 in this case. Now you could also use another function called linear solve, which actually uses matrices. So you can take the same system and form the coefficient matrix, which is 1, -2, 1, 0, 2, -8, and -4, 5, 9. Form the coefficient matrix. Put on the right-hand side, B, 0, 8, -9. Give it a linear solve. You do A comma B, and you get back the solution. The same solution as before, but now x is 29, y is 16, and z is 3 has to be read off. And those entries over there are the x, y, and z. Okay, so that's a second way, the linear algebra way of doing things. But a third way to do the same thing is to use a so-called row reduce function. So row reduce says take both the left-hand side and the right-hand side and put them back into the augmented matrix. That's B over here. Here's the matrix form. And it looks quite messy, but if you apply row reduce to it and then do a matrix form, the percentage means you're doing the matrix from the previous output, then you see that in fact it looks very nice and clean. And keep in mind that this one over here is a placeholder for x. So x is 29, y is 16, and z is 3. So the entries in the last column over here will now give you x, y, and z. So row reduce is a bit harder to understand, but in fact it's quite a powerful function. Okay, so that brings me to the end of the lesson. So basically we have talked about systems of linear equations lesson, and you can always use matrices to represent such systems. And there are 3 ways to solve them. You can use solve, which is kind of the classical way to solve the equations. But if you're doing linear algebra, you probably want to use linear solve. Or you might want to use row reduce, but that's a little harder to understand. So in the next lesson, we'll talk about row reduction and echelon forms to try and understand how to use the row reduce function at a deeper level. So I hope you have understood the basic concepts in this lesson quite well, because they are fundamental for everything that follows. I'll stop over here. Thank you very much.